Thanks for joining Crystallon simulation with Millipede. What I'm going to show you today is going to be just a quick overview of Millipede and its capabilities. I want to show you how to use simulation to guide the design of lattice structures. But first I want to talk a little bit in this presentation about what is FEA and why anyone interested in lattice structures should try to learn about it. There's different types of simulation, and Millipede is one of the best, and it's ideal for lattice structures. And lastly, I want to talk about how we can use it to optimize the design of our lattice structures. So I'm going to go through some slides first to give a bit of an introduction, and then I'll do some quick demos at the end. Then I'll do the Raffle drawing to select the winner of 50% off the course. And at the end, I'll try to leave some time for questions and answers. So let me start by telling a little about myself. I'm an industrial designer. I'm from San Francisco. I have about 8 years professional experience in design for additive manufacturing. I have quite a bit of experience using Grasshopper for my design work, and it's actually become kind of the main tool for most of my work. And that's kind of why I developed Crystallon. It was kind of a set of tools I used for my own design work, and later I decided to share them open source. The points I want to make first is I'm not a software developer. I'm just a designer sharing his tools. And more importantly now is I'm not an engineer. That said, I have worked very closely with engineers for a long time, and I've bothered them enough to learn a few things. So what I want to teach you is what I've learned from my engineer friends, basically by bothering them and making them show me how they do what they do. And just kind of a basic understanding of simulation for designers. I won't be trying to teach you any fundamentals of engineering here. Instead, I kind of want to show you just how FEA can be useful for a designer, especially if you're interested in lattice structures. So I spent the last month working on an online course that's available now on Vimeo. You can find the link to the course in the description of this video. It's a 3-part video series about using Crystallon with Millipede. It's only $100 for all 3 videos, and you get the rental for a year. So it's affordable, and you'll have plenty of time to watch it as many times as you want. The reason I chose to do videos rather than live webinars is because I felt like most of the people interested are kind of in different parts of the world and different time zones. So it doesn't really make sense to do it live when people would be watching at 2 a.m. So this way there's no interruptions. It's just all useful information. And you can watch it as many times as you want over and over for a whole year. So part 1 is just a basic overview of using Millipede. And that's for those with little to no experience using FEA. So we learn about basic setup, setting up a basic simulation using Crystallon and Millipede. Part 2 is about different techniques for optimization, and this will include the optimization tools within Millipede as well as using some evolutionary solvers like Octopus. And then part 3, we take what we learned in the previous lessons and apply it to a real-world scenario, which will be a brake pedal. So today I want to give you a little preview of what we'll learn in the course, but first I want to go through a few slides real quick. I won't bore you too much, but I want to give you a quick introduction about what is FEA and why you should be interested. So if you're interested in using lattice structures in your design, you should probably be interested in learning FEA as well, because the only way you can know if a lattice design will be effective is to test it. So obviously this could mean trial and error of building prototypes and physically testing them, but that can be really slow and expensive. And so this is why engineers use FEA to simulate how a material will react under certain conditions prior to doing any physical prototyping. So to describe FEA very simply, FEA stands for finite element analysis, and finite meaning there's a known number of elements in the model, and each element can be calculated based on its material properties. So the process goes a bit like this. A model needs to be broken down into many smaller elements, and these elements have a shape or a thickness, and each element has material properties. Supports are how elements are constrained to a specific space, like for instance this cantilever beam is fixed to a wall. And loads are forces that are applied to these elements, which are the forces we want to test for. Then the solver can compute how those loads are applied to each element using the finite element method, and it produces results. And these results include displacements, stresses, and internal forces on each element. So if you're used to using a solid modeling software like SolidWorks or Fusion 360, you might be familiar with this kind of simulation, which is more for mechanical engineers. So mechanical engineers will usually take one part of an assembly to test under certain loading conditions. And in order to do this, the solid model needs to be broken down into thousands of smaller elements, a process called meshing. And this is to make a volumetric mesh of solid elements. And these elements are usually one of two different shapes. They're usually either a tetrahedron or a hexahedron. Then the solver can compute the material properties of each element that make up that whole model. And this way an engineer can see what elements in what part of the model are under the most stress and make decisions based on that. But now structural engineers need to simulate loads on an entire assembly of a building at once. So in this case it might be a lot of steel beams and concrete slabs. Using the same process of meshing each part into solid elements would be a very slow process and probably require some kind of supercomputer. So in order to simulate such a complex structure, the types of elements they use need to be simplified. So since a steel I-beam doesn't change shape along its length, it always has the same cross-section. Mathematically, it can actually be simplified into a single element in the solver. So different FEA packages will support different kinds of elements for different kinds of simulations. And Millipede is a structural engineering plugin, so it only supports beam and shell elements, which are actually ideal for us. Beam elements are simply a line between two nodes with a cross-section, and shell elements are simply a surface with thickness made from 3 or 4 nodes. So when it comes to simulating such a complex model like a lattice structure, we need to start simplifying it, make it simpler. Beam and shell elements are actually much better suited for simulating lattice structures because dividing a lattice into many smaller solid elements would take a lot of computing power. So imagine how many 3D elements it would take to mesh one beam of this lattice, and now multiply that by the number of beams. Since a lattice structure is typically made up of just interconnected beams and surfaces with kind of usually a uniform cross-section, we can simplify the model into 1D and 2D elements. And then we can simulate a much more complex design with a lot less computation time. So if you don't already know, Crystallon is an open source toolkit for generating lattice structures. One of the most important things I took into account when making it was modularity, to work together with other powerful plugins. So I wanted to make sure that during any part of the design process, the outputs are compatible with other plugins such as Millipede. So Crystallon will always output your lattice as either single line beams, meaning lines between 2 points, or as a mesh surface, which can be used as shell elements. Then after a simulation, the results from Millipede can be used again with other Crystallon components, like the thickening tools or other things. So finally, let's talk about Millipede. Millipede is a very powerful plugin for Grasshopper for everything from structural simulation to topology optimization. Unfortunately, it's been discontinued since 2014, and it's only working on Windows, so sorry to the Mac users. I actually don't know of any good simulation plugins working on Mac at the moment. And as of now, actually, in the middle of making this course, the website seems to be down and the download page is gone completely. And this is sad because it was such a good tool, but this tends to happen when people develop a tool for free and then get too busy to maintain or update it. So that said, for this course, I have the original installation files included in the demo files on the course. So it's not gone forever, but if you do download them, please just follow these rules. You must read the included license agreement that you agree to when downloading it. and I'm not reselling or relicensing the software. I'm only hosting it as is under the original license agreement. So it's not gone forever. If you want to take the course, you can still get Millipede, but it's too bad for this situation. So moving on, let's talk about what Millipede does. It has a lot of powerful tools, not just FEA. It has tools for creating ISO surfaces, minimal surfaces. It can optimize mesh topology. It can also do 2D and 3D topology optimization. And also a lot of these tools can work together in really interesting ways for optimizing all kinds of designs. In this course, we'll just be covering the basics, just FEA tools in Millipede, but be sure to download and read the PDF documentation that talks about all the other powerful tools. So first, I should talk about what Millipede can't do. So Millipede is a static linear solver. So it's only really helpful for structural applications. Linear means it only works well with linear materials. So what it can't do well is simulate flexible materials with large deformations. So it wouldn't be good for applications like energy absorption. Ideally, you would want to use a nonlinear solver. Nonlinear basically means the simulation is iterative and it recalculates based on the results of the last step. Also, it's only a structural solver, so it can't do other physics like fluid dynamics or thermal properties. So it's also not the right tool for things like heat exchange. That said, I do talk about some other affordable tools for more complex simulations in the third video of my course. But if you're just getting started with FEA, Millipede is free and it's a good place to start. So what does it do? What Millipede does really well is structural analysis, and it does it really fast. So what's nice about being able to simulate a model very fast is we can actually iterate much quicker. We can actually change the parameters of our design and see the simulation results in real time. So having a parametric FEA tool as part of our design toolkit means we can test the structure while we're designing it, which is something you can't do in other software very well. And since it can simulate so fast, it can also be used in conjunction with things like evolutionary solvers. In part 2 of my course, I'll talk about how to use Octopus with Millipede. Octopus is a multi-objective evolutionary solver, and it can iterate through thousands of results to help you find the optimal parameters based on your goals. So we could iterate through things like unit cells, cell size, thickness, or basically any parameter you want to find the optimal solution for any number of goals. And our goals could be anything. For instance, we might have 2 goals: find the stiffest structure with the least amount of mass. Octopus also has tools for machine learning, so it can help you guide the optimization based on selected results. I won't be covering the machine learning neural network stuff during this course, but I might do one in the future. So Millipede also includes its own optimization tools, and these are like topology optimization, but used with beam and shell elements. And I'll talk about the difference in my course. This way you can optimize the thickness of each element based on loads applied to them. So I'll show you how to use these in part 2 of my course, and we'll learn how to use Millipede's optimization tools on a lattice and validate those results to be optimized for additive manufacturing. So I went through that pretty quick, and I know you're all are waiting, so let's do some quick demos. Let me open up Rhino real quick. So this is kind of the final file that you'll be using in the course, and it's quite simple actually. For the introduction, I really just want to show how to simply simulate a structure. And so we start by just kind of making a structure that's sandwiched between 2 surfaces. And so we're almost doing like compression tests. Imagine it's just a lattice with a load on top of it. So I apologize if my computer goes a bit slow, because while I'm streaming or recording, it gets a bit slow, so I might not be able to show you exactly how fast this really goes. But let's see. So to begin, I'm just simply morphing between 2 surfaces. And these are actually some tools that aren't included in the latest Crystallon. They're on the GitHub site if you want to download them. And what this one is doing is basically just dividing a surface into a mesh. And the reason I'm doing that is so I can use morph between meshes, but then I can also get the mesh edges of those and use those as elements as well, almost like a skin. So this is the lattice structure we create, and so I've got divisions both in the X, Y, and Z directions. So it is going to go a little slow for me, so I apologize for that. So to start, I'm just going to go with a simple, just start simple here so we can see fairly quickly. So the output of Crystallon is, of course, we have these 24 line-like curves, and these are just lines between 2 points. And so to create elements in Millipede in the FE system toolbar, here's all our things to set up an FE simulation. So we have our elements. We can define them by a line between 2 points, or we can actually use a curve, and that's what I'm doing here. And this way we can just input curves, and if it's a NURBS curve, it'll divide it into a polyline and make each of those segments elements. But in this case, just these lines are becoming our elements. And now actually I should show you first also, I'm also creating a shell lattice structure between these two surfaces to show how to simulate shells, but I won't be doing that in this video, but this is how it's done. We can just input a mesh to create our elements. So each element, now that we have our lines, we need to beam elements need to have a cross-section. So in the stock tools, we have the cross-section component. And if we right-click on it, we have all these different cross-sections we can choose from. Since I'm typically simulating things for 3D printing, I use just the solid circle cross-section. Because typically we're going to make round, cylindrical type of beams when we 3D print these. We could do others, but at that scale it's not really necessary. So with that cross-section, our only input is just a radius. And so that's what I have here. I have my radius, or this is actually my diameter, and I'm dividing by 2 to make my radius because I use the same thickness for the shells. Now shells is just a surface with thickness. And then lastly, each element needs to have a material. So what I've done here is I've made a custom material, but if you go to the stock dropdown, you can select from different preset materials like steel, high-strength steel, concrete, aluminum. But what's going on here, if I add a panel, we can see these are just the material properties. We have the elastic modulus, the Poisson's ratio, density, and that's exactly what I've inputted here. So you can find data sheets for pretty much any material you want. Remember, it needs to be an isotropic material. And isotropic material means it has the same properties in every direction. So something like wood, where it's weaker depending on the direction of the grain, you can't really simulate that very well here. But here I just took a data sheet I found online for SLS 9-on-12. And then next let's talk about supports. So there's a couple different ways we can make supports. We can use a region where we could basically say I want to create a boundary, like create a box over this, and any nodes within that boundary become supports. But instead what I'm doing is actually defining my supports by specifying the location of the point. And so what I do is I actually just find all the unique points in this model. And then what I'm doing is just finding the ones closest to the surfaces. So I'm saying the points that are touching this bottom surface I want to be our supports, which are these. So now we have these 4 support points down here. And the reason I have 2 different supports going on is you can see here, and what this is the boundary conditions. So boundary conditions define how a support is fixed to a certain place. So These Boolean values are basically if it's free to translate in the X, Y, or Z direction, and if it's able to rotate in the X, Y, or Z axis. So what I'm doing here is I actually have one point supported one way and the other three supported another way. And I'll show you what kind of difference that makes afterwards. And lastly, loads I set up pretty much the same way. Loads, you need a location of the load, and then the load is actually just a vector. So you create a vector which is a direction, and the amplitude is the amount of force in newtons. So what I've done is actually just found those points that are touching this top surface, these here. And then for the vector, the direction I want, I just made them normal to the surface. And the reason I did this is, say if I have this surface and I rotate it, my load will change, right? So I just made it kind of a bit more parametric by using the normals of the surface. But in this case, we're just going to be putting our force kind of in the negative z direction, just to start. And so now we have our elements. I'm using just these beam elements now. The shells are disabled. We have our supports set up, and we have our loads. So all of that goes into the system builder, and the system builder is basically taking all our elements, our points, our supports, and our loads, and it makes unique nodes from each of those. And you can also have different load cases if you want. And basically, that just creates an FE system that goes to the solver. If I enable this, now we can see we get some results right out of the solver. We get the amount of deflection and we get the amount of weight. What I'm doing here is actually because Millipede is assuming that all units are in meters. So even if you're working in millimeters in Rhino, the calculations that Millipede is doing is assuming those units are meters. And that's why I'm multiplying my load times 1,000 from newtons to kilonewtons. And in the end, for my weight, I'm calculating basically from kilogram per cubic meter to grams per cubic millimeter. So now we want to just visualize our results, and we can use the frame visualization component. And so if we preview this, it's already simulated this model. There's nothing we need to change. I'm going to go ahead and just play with the material, our beam diameter a little bit, so you can see what happens as I do that. So right now I'm visualizing deflection, and actually the deflection I don't have all the way up. This number slider is the amount to show deflection from 0 to 100%. So let me give this a little more thickness so we don't have a little pancake going on. Right. So that quickly we can, in real time, see our results. Now this is going especially fast because we have very few elements, but even with quite a bit more elements, it can go pretty fast. So let me go ahead and just hide the original curves so we don't have to look at those. We don't have to look at these surfaces. And I'll just keep these points showing, these vectors. So in our visualization, we can see a lot of things. We can see deflection. We can see axial loads. So you can see red is compression, blue is tension. And I'll show you right now I actually have these mesh edges from our surfaces as part of the elements. If I disconnect these, I'll show you what difference that's going to make. So we got quite a bit more deflection now. Let me give it a little more beef. There we go. But now you can see nothing's in tension, everything's in compression. Let me simplify this model even more. Now we're just one unit cell. So we can see axial loads, we can see the bending moment. The bending moment obviously is at the node. Normal stress is kind of combined axial forces and bending moments, so we can see. And yield is nice because when we define our material, we can define our yield strength. So in this case, 48 megapascals is the yield strength of this material. And what Millipede will do is show it'll show red where the material is yielding, but then it also gives you this complete range. And the number 1 would be 100% of the yield strength. So right now this model would break. Let me make this a little thicker so it's not yielding. But basically we can use this to basically see our safety factor. So if we want a safety factor of 2, we would want the yield to be under 0.5. And that's a quick way, rather than looking at the overall maximum internal forces on each beam, we can just see overall our safety factor right there. And we can see deflection. What I wanted to show you real quick is, let me make this a little thinner so we see a lot of deflection happening. I want to show you how changing these boundary conditions actually changes our model quite a bit. So right now it's kind of moving freely on the bottom surface, and that's because these supports I have free to move in the x and y direction, and they're also free to rotate in the x, y, and z axes. I leave them fixed from moving in the z direction because obviously then they would just fall through space. And then the 1 point that I have fixed in one position. And you can see how this icon changes when we change these boundary conditions. So let's say if I made it true, I want them fixed. Now we can see this changes our simulation quite a bit. So now when we look at the deflection, that force is really just focused on those top beams. If we look at the axial loads, still everything's under compression. But let's say I allow them just to move in the x direction. Now they're able to move this way, and allow them to move in the y direction. So in this setup, it would be more like the bottom points are fixed, like they're stuck in the ground and they're not able to move. But in this configuration, it's almost like a freestanding structure, where say it's like a little lattice that you put on a table and pressed on it on top. So it's important to know about boundary conditions and get the boundary conditions right in your simulation, because that's actually going to affect your results quite a bit. So what else I wanted to show you is Octopus. And so Octopus is this guy here. If you're familiar with Galapagos, it's very similar. And what it can do is I have genomes set up, and I'm setting up the different divisions, cell divisions, as my genomes. And these are the parameters I want to play with. And then the goal, what I want to see is I want to see the minimum deflection and the minimum weight. And so what Octopus can do is actually it can run through these very quickly. And I'm going to see how quickly it actually does it here. It might go a bit slower on my computer now since I'm streaming. But actually it's only taking like 300 milliseconds per result, so it's going a bit faster since I tested before. So what it's doing right now is just making one population, one generation of a bunch of random parameters, and it's going to make 200 solutions in that first generation. And then what it's going to do in the next generation, it's going to find the most fit, I want to find the least deflection and the least weight, and it'll find the solutions that fit those criteria the most, and it'll basically take those parameters that made those solutions and mix between those to find the next best ones. And it'll keep going as long as you want. I'm not sure how long I'm going to let this go, because it seems like it's starting to get slower. So I might not let it run very long during this demo. it's going to take too long. So anyway, I'll stop it here. But basically now we can see our results, and we have this graph. And it's a 2D graph right now because we have two goals. If we had more goals, we could have this third axis. We could have them change color or size. But if I just want to look at the results, now we have some of these results we can look at. And you can see this is the highest deflection with the least weight. And this is the least deflection with the most weight. And if I just click them and say reinstate solution, and that's the one that takes the longest because it's the most elements. So I'll try not to freeze the computer anymore during this. But let's take a look at some other solutions, like this one. So if I had let this run for a long time, well, it wouldn't even take that long, maybe 5 minutes to go through a lot of generations. We could actually find pretty close to what the optimal results are. Another way we can look at it is multi-ax view. And here we have kind of two lines, the deflection and the weight, the minimum and the maximum, and you can see all the results here are these lines, where one is kind of minimum weight, maximum deflection, maximum weight, but the top is going to be minimum of both. And so that was the best solution it came up with in that short time I gave it. So that's all I'll really show for Octopus for now. The other thing I wanted to show you really quickly is how to do beam optimization with Millipede. So what I'll do real fast is I'm going to give this a few more divisions just to make it more interesting. So now we have this structure, but let's say right now they're all this diameter, like 0.3, and oops, I want to change this to 0.3. Let's say all these beams probably don't necessarily need to be all the same thickness to have all the same strength. And so that's what's nice about Millipede, is it can do basically what's like a topology optimization, but it's looking at stresses on beam elements or shell elements. So it's a bit different from your typical topology optimization, where we're working with solid elements, or basically voxels, you could say. But let me show you how this works. So if we visualize stiffness factor, and we set the number of iterations we want to do to say 1, you'll see this guy pop up, and this is a little status bar. So I can click step a bunch of times, and you'll see it slowly begin to do its work. And this will look a lot like a topology optimization. And then what we actually could do, since this is a pretty simple model, even though my computer is going a bit slower right now, what I'll typically do is just set the number of iterations to something like 50 and just let it go. This might take a moment with my computer going slow, but actually no, it's not so bad. So I have optimization scale turned on. If I turn it to false, these are the results we get. And so it's basically saying the black beams are least important, the white beams are the most important. We don't have a lot of variation in here actually right now. If I turn op scale on, it's basically just scaling these beams based on their color. We can change our optimization target, and this is kind of the target mass you want to optimize to. So say you want to get it to half its mass, you might set that to 0.5, and that's going to give you these different results. And so how do we actually use these results is actually what's most important, because the data we get, if we look at all our results from our beams, we have our forces, our bending moments, estimated max stress for each element, and then we have this stiffness multiplier, and this is the value that it's given that beam, and it's just a number from 0 to 1. And so what I typically do is I run a whole nother simulation with the same boundary conditions, the same load, the same supports, but I make new beam elements here, and with the same material, but I change the radius, and what I do for the radius is just remap these values, these numbers from 0 to 1, to a new range of numbers. And the reason I do this is because this is typically where you would say, this is where I want this is the minimum radius I can actually 3D print, and this is the maximum radius I actually want to 3D print. And then we can optimize these beams. We can apply those values, and we can see if those results are valid, if it's going to be strong enough. And I'll show you how I do that here. So if I enable this, and I'll hide this one so we don't necessarily need to see it anymore. So now we can change those values. And then this is actually another simulation happening in real time, so I could visualize, say, my axial loads on this model. I can look at usually what I'll do is just look at yield strength in the end. I want to optimize, I want to have the same yield strength as the original model. And then you can go and you can change your values and see how thin can you actually make these before it begins to yield. And this, again, is where you could use Octopus again to basically run these values, your thickness values, as parameters. And again, look for the least deflection and least weight. And you can also add a Boolean value as a goal. And that's what I'll usually do here, is basically I want to see if the yield strength is under 1. And if it's true, it's a valid result. If it's false, Octopus will just ignore that result. And another thing we can do is say, let me preview these so we can see the beams a little better. Oops. I want it previewed, but I'll look at none so we can see these a little better. So these little beams, right now they're at 0.1 millimeters or something like that. So we might not even be able to 3D print these. And they might not be necessarily at all. So what we can do is just filter those least important beams out of the simulation. And what I'll usually do is filter out, say, the bottom 10%. And now we have a model like that, where we filtered out the least important beams. And then we can play with these thicknesses to, within a range that we can actually print. And again, we can look at the yield strength and do another simulation or another Octopus optimization if we like. So that's basically what I go over in the first and second videos. The first video is basically learning all about setup, more in depth, how to find material properties, what are good material properties to use, how we change boundary conditions, and how to set up loads. And the second video is more about using Octopus, and I go a bit more depth in there, and using the Millipede's optimization tools. In the second video, I'll just show you guys this real quick. We want to start with a case study, which is basically going to be this brake pedal. So this is the original model that we start with. And I simulated this model in another software to get kind of a baseline results that we want to beat. We want to get lighter with the same strength. And what we start with is actually playing with just the divisions. And so what I do here is I'm using, again, another component that's not released in the latest Crystallon, but it is on GitHub. It's in the version 2.1 folder. But this is basically making it's basically like the graph mapper. It's reparameterizing values based on a curve. And I'm creating this NURBS curve from points. And the reason I want to use points to make these curves is because then I can use Octopus to change these values. And so if you see, if I move these sliders around, I'm changing this curve, and I also like to have kind of a gradient view to see how that gradient looks. But what these curves are doing is actually changing the divisions on the surfaces. And so what's interesting is the orientation of a lattice structure is actually quite important. Having beams in line with the flow of stress makes a much more efficient structure. So this is kind of where a lot of lattice software kind of doesn't let you do. You might be able to make something morphed between surfaces or conformal to surfaces, or some of them just kind of fill a volume with a lattice. But being able to actually optimize for the optimal orientation, the direction of these beams, can actually make quite a bit of difference in how efficient the structure is. And so that's what we do here, is we change the divisions, and we use Octopus to kind of, we have 8 different values we can play with to kind of just change the divisions to change the orientation of these beams and find the optimal orientation to be the stiffest structure. And we can actually, I'm not sure how fast this is going to be while I do it. I don't think I'm going to try using Octopus now because everything seems to be going pretty slow. So let me hide this mesh. So now we can look at like the stresses. So basically we're making this brake pedal out of an internal lattice and kind of 2 mesh skins on the outside. And we can change these parameters and see how that affects, you know, the strength of the structure. And then we do basically the same kind of, we do another beam and shell optimization. We do it with beams and shells, and we validate those results. And then we use Dendro to create a 3D printable file from these results. And I actually do some modifying of the mesh a bit to make it a bit cleaner. And then what you need to be able to do is kind of validate the results of your final STL mesh, and that's kind of where a lot of software falls behind in, is because once you create this, like in topology optimization, it's hard to actually create this mesh model and then simulate that mesh afterwards. So I show you very briefly in the video how it is possible. You can actually take a mesh from Dendro, triangulate it better, make a volumetric mesh with solid elements, and you have to use another software to simulate it, and I use Mechway, and I'll show you in the video. But I think that's about it that I'm going to show you guys today in this video. Let me just check to see if there's any questions right away that I should answer. No? Okay. So, I think what I'll do next is I'm going to run through this raffle. So if you guys took part in my survey, you entered a contest to win 50% off the Millipede course. And so what I've done is I've created a little raffle definition. And so what I have here is kind of the Excel file, CSV file that's with all the results. I've got all your names here. So I had 31 entries. And then what I'm doing is I've got a little dice here that I'm going to roll, and I'll show you how this works. I have a timer connected to it, so it's creating a new random number every 20 milliseconds. And I'm just going to stop the timer to find the winner. So if you guys are ready, let's start the competition. So let me start the timer, do a drum roll. And 3, 2, 1. Roberto, you are the winner. So I'll be sending you an email with a discount code for 50% off the full course. All right, so let me go back to my slides, and so that's all I've got to show you today. Thank you so much for joining. If you have any questions, feel free to email me at info@f=f.com. You can see more news on our blog at www.f=f.com. And if you're interested, please buy the full course. Be sure to subscribe to this YouTube channel to keep up to date on new videos or new live streams. And that's all. Thank you, guys. Oh, we've got one question. So someone asked, before I stop, someone asked, some of the deformations are pretty large. Does the program handle large deformations? And the answer is no. No, something like Karamba can do large deformations, but you need kind of an iterative solver. You need something basically nonlinear to look at large deformations. So it's not great for that. It's really just a linear static solver. Another person asked, maybe this is a silly question, what's the difference between Millipede and Karamba? They're both structural analysis tools. Karamba is quite a bit more advanced. You got a bit more tools, but the setup is very similar. Karamba has a few different algorithms, so it can do like Besso beam optimization, things like that. It also has kind of a beta nonlinear solver, so you could look at large deformations, like another person was asking. I'm working on doing a workshop with Karamba, so I'll have more information on that. So hopefully I'll have a workshop going on with them fairly soon, in the near future. I'm just going to wait a moment to see if there's any more questions. Nope. Okay. So thank you all for joining. Thanks for your interest. I hope you found it all useful, and I hope you're interested in taking the full course. So thank you all for joining, and feel free to email me if you have any more questions. All right, bye.